let's analyze this another problem where we are given an electric flux density D of 0.3 radius square in the AR direction nanocoulombs per square meter in free space, and we are asked to obtain four different things. First, the electric field intensity at a given point, the total charge within the sphere of radius equal to 3, the total electric flux leaving the sphere of radius equal to 4, and the volumetric charge distribution at any radius rho b. So let's get started with the first part. Well, we know what is going to be the flux density given by the problem. And we know there must be a relationship between the flux density and the electric field intensity. That relationship is given by the expression flux density equals to permittivity of vacuum, in this case, times the electric field intensity. If we want to obtain the electric field intensity, we solve for E. E equals to flux density over permittivity of vacuum. That's going to be equal to 0.3 radius square in the AR direction nanocoulombs per meter square. However, since we're working with nanocoulombs, we can actually easily take out this part and play the full expression times 10 at minus 9 r squared in the AR direction. And we set the units as coulombs per square meter. We have already our expression for electric field intensity. We are being asked to analyze at one point. This point is composed by the polar or spherical coordinates radius equals 2, theta equals 25, and phi equals 90. However, when we see the expression for electric field intensity, there is no theta, there is no phi. That means the electric field intensity will only depend on the radius. Keeping that in mind, the electric field intensity at a radius equals to 2, it's going to be 0.3 times 10 at minus 9, 2 squared in the AR direction, and that's going to be over, I was missing what part, this is going to be over epsilon 0. When we place this over epsilon 0, we change from coulombs from square meter to volts meters, or newtons over coulombs. Any one of those two units can be valid. So we analyze from here, adding the component of epsilon 0 in the AR direction. That's important. When we replace all the values, we will obtain that the total value of the electric field at that point is going to be 135.53 times 10 at minus 9. Whoa, no. It goes directly like that. Remember that E equals to 8.854 times 10 at minus 12 farads meters. Keeping that in mind, I am dividing by a number very, very small, and we already have a number small, so I should expect something like this. I can express it in the units I want, so I'm going to do it in the volts meters, and that's giving me exactly the same as if I made it for newtons over coulombs. It's going to be exactly the same, this one as this one, in the AR direction volt. That's going to be for the part A.